Hello my dear students, welcome to WBJEE YouTube channel. So today we are going to solve NCERT textbook, and this is chapter continuity and differentiability, exercise 5.1 from class 12 textbook. So today we are going to solve question number 1 to question number 5. So let's start. So before solving the exercise, let us first recall what continuity is. So fx is a function. Fx is continuous at x equal to a if some conditions happen, that is limit x tends to a plus fx and limit x tends to a minus fx and f of a. These three terms are equal, then we say that fx is continuous at x equal to a. So what does it means that x tends to a plus? That means this is a and x equal to a. So x tends to a plus means x is tending to a, x is tending to a and x is greater than a. X is tending to a and x is greater than a. This means limit x tends to a plus, and this is x equal to a and x is tending to a and x is less than a. This means that limit x tends to a minus. And what is f of a? In the expression f of x, just put x equal to a, that is f of a. And if these three are equal, then fx is continuous at x equal to a. So now let's start the exercises. Exercise 5.1, prove that the function fx equal to 5x minus 3 is continuous at x equal to 0, at x equal to minus 3 and at x equal to 5. So let us check at x equal to 0. So we have to check limit x tends to 0 plus fx, and the definition of fx is if 5x minus 3. So 5x minus 3 and limit x tends to 0. Now put x equal to 0 minus 3, that means minus 3, and also x tends to 0 minus fx. There is one definition for fx, so we will replace everywhere fx as 5x minus 3. So limit x tends to 0, 5x minus 3, it is also minus 3, and f of 0, is 5 into 0 minus 3, that means minus 3. So you can clearly see that limit x tends to 0 plus fx equal to limit x tends to 0 minus fx and f of 0, all are equal and equal to minus 3. So therefore fx is continuous at x equal to 0. CTS means continuous. Now at x equal to minus 3. So we have fx is 5x minus 3. Now we have to check at x equal to minus 3. So again we will check x tends to minus 3 plus fx. Observe that this x is minus 3. So this is minus 3 and we are approaching to minus 3 from the right hand side. So that means x tends to minus 3 plus. So that is equal to limit x tends to minus 3, 5x minus 3. So put x equal to minus 3. So that means 5 into minus 3, that is equal to minus 18. And also limit x tends to minus 3 minus fx equal to limit x tends to minus 3, 5x minus 3. That means equal to 5 into minus 3 equal to minus 18. And f of minus 3, it is also equal to minus 18. So therefore limit x tends to minus 3 plus fx equal to limit x tends to minus 3 minus fx and f of minus 3 all are equal to minus 18. So therefore fx is continuous at x equal to minus 3. So for x equal to 5 we will get f of 5 equal to 22 and limit x tends to 5 plus fx, this is also equal to 22, and limit x tends to 5 minus fx, this is also 22, and hence fx is continuous at x equal to 5. Okay, so next problem, examine the continuity of the function fx equal to 2x square minus 1 at x equal to 3. So we have to check limit x tends to 3 plus fx. What is the definition of fx? Fx is 2x square minus 1. So that means limit x tends to 3, and in place of fx we will write 2x square minus 1, that is equal to 2 into 3 square minus 1, that means 2 into 9 minus 1, that is 17, and also x tends to 3 minus fx, this is also equal to limit x tends to 3, and the definition of fx is 2x square minus 1, that is equal to also 17, and f of 3 is also 2 into 3 square minus 1, that means equal to 17. So therefore limit x tends to 3 plus fx, this is equal to limit x tends to 3 minus fx and f of 3. So therefore fx is continuous at x equal to 3. Observe, in the previous problem that was 5x minus 3, and this is also 2x square minus 1, and observe that these two are polynomials. So from this we can conclude that the polynomial function is continuous throughout the real numbers. Next problem, problem number 3, examine the following functions for continuity. So fx equal to x minus 5. So for this, limit x tends to a, where a is any real number, a belongs to R. So fx is equal to, this is limit a minus 5, and also limit x tends to a plus f of x, this is also a minus 5, equal to limit x tends to a minus fx, this is also a minus 5, and f of a also a minus 5. That means for any a belongs to real numbers, fx is continuous. That means fx is continuous on the whole real number on R. Now fx is equal to 1 by x minus 5 and x not equal to 5. That means we exclude the 1 by 0 form, and this function is also continuous on whole R, because these two functions are polynomial functions, or rather this function is rational function. And now this is fx equal to x square minus 25 by x plus 5 and x not equal to 5. Check that limit x tends to a, fx is equal to x minus 5, that means a minus 5, and for all a belongs to R. For any a that is a real number, this fx, limit x tends to a, fx is a minus 5. So that means this would be limit x tends to a plus fx, and also limit x tends to a minus fx and f of a. These three are equal, and that is a minus 5. So this is continuous on whole R. Now the problem number D. This is something interesting. So problem number D is fx is equal to mod x minus 5. mod x minus 5. So we have to break this definition. So that means this is equal to x minus 5 if x greater than 5, and 5 minus x if x less than equal to 5. We can use the equality sign in case of x greater than 5, but we use here. So now check the continuity of this function. Observe that when x not equal to 5, that means x is any real number not equal to 5, then the definition is either x minus 5 or the definition is 5 minus x, according as x less than 5 or x greater than 5. When x is less than 5, then the definition is 5 minus x, and when x is greater than 5, then the definition is x minus 5. But for x equal to 5, let us take x equal to 5. When we are approaching to 5 from the left hand side, that means x less than 5, then the definition is 5 minus x. And when we are approaching to 5 from the right hand side, that means x greater than 5, then the definition is x minus 5. That is, we have to check the continuity of this function at x equal to 5, because for that x equal to 5 we have two different definitions. So now let's check limit x tends to 5 plus fx. So x tends to 5 plus means x is greater than 5 and x approaching to 5. So that means that is equal to limit x tends to 5. For the place of fx, we will write x minus 5. So that is 5 minus 5 equal to 0. Now limit x tends to 5 minus fx. This is x less than 5 and x tends to 5. That means limit x tends to 5. In the place of fx, we will write 5 minus x. So that means 5 minus 5, that is equal to 0. And place 5 in any of the definition, f of 5 equal to 0. So clearly you can see that limit x tends to 5 plus fx and limit x tends to 5 minus fx, and also f of 5 is equal to 0. That means these three are equal. That means therefore fx is continuous at x equal to 5. And we also have seen that x for x not equal to 5, fx is continuous. So that means fx is continuous on whole R. Okay. Now next problem. Problem number 4. Prove that the function fx equal to x to the power n is continuous at x equal to n where n is a positive integer. That means n belongs to natural number. N is a positive integer means n belongs to natural number. N is a natural number. So limit x tends to n plus fx, and we have only one definition. For x greater than n or for x less than n, we have only one definition. So limit x tends to n, x to the power n, that is n to the power n. And this is also equal to x tends to n minus fx equal to limit x tends to n, x to the power n, that means n to the power n, and also f of n equal to n to the power n. So that is limit x tends to n plus fx. This is equal to limit x tends to n minus fx and f of n. So that implies fx is continuous at x equal to n for all n belongs to natural numbers, because n is a positive integer. So that means n is a natural number. So here you can also observe that x to the power n is a polynomial. Okay. So we have already told that polynomial is continuous in the whole real number. So next problem is the function f defined by fx equal to x if x less than 1 and equal to 5 if x greater than 1, is continuous at x equal to 0, at x equal to 1, at x equal to 2. So now check first at x equal to 0, at x equal to 0. So we will not check all the values, because limit x tends to 0 plus fx, this is equal to limit x tends to 0 minus fx, and also f of 0. These three are all equal to 0, because for x less than 1, that means x less than 1 means x equal to 0, which is less than 1. So for this, the definition is fx equal to x, that means all are equal to x, and x equal to 0, that means all are equal to 0. And for x equal to 2 also, limit x tends to 2 plus fx equal to limit x tends to 2 minus fx, and also f of 2, all are equal to 5, because for x greater than 1, the definition fx equal to 5. That means for these two, fx is continuous. That means fx is continuous at x equal to 0 and x equal to 2. But for x equal to 1, we have to check. Now limit x tends to 1 plus fx. That means what? We are approaching to 1 and x is greater than 1. That means from the right hand side. So for the definition, we will use the definition for x greater than 1. This definition is 5. That means x tends to 1 plus fx is equal to limit x tends to 1 and 5. So here x is absent. That means this limit will be 5. Now limit x tends to 1 minus fx. That means we are approaching to 1 and from the left hand side. That means x is less than 1. And for less than 1, the definition is fx equal to x. So that means limit x tends to 1 x. That means 1. And we will not check that f of 1 is what. And for this, f of 1 is also 1. But observe that limit x tends to 1 plus fx and limit x tends to 1 minus fx, these two are not equal. That means this implies that fx is not continuous at x equal to 1. Hope you understand all these problems. If there is any problem, let me know in the comment section, and I will solve from 6 onwards in the next videos. Thank you.